So in the same way that we took what we knew about the gravitational force and used it to talk about the gravitational field, we're going to take what we know about Coulomb's law and what it tells us about electric forces to build what we're going to understand about electric fields. So the question becomes, how do we learn about electric fields? And for starters, here's sort of our basic explanation here. We're going to start with a charge Q. There it is, sitting out there in space. What we're going to do next is we're going to bring some test charge and we're going to put it at a point P. So here's our point P, and you can see the line that connects point P to our charge, big Q. And so I'm going to bring in my test charge and place it there at point P, and I'm going to measure the electric force that big Q, which is my source charge, exerts on Q naught, which is my test charge. So I'm going to care about that force that I know how to measure through Coulomb's law. And so what I'll do then is say, well, in the same way that we said that with the gravitational field, we didn't want that to depend on the test mass, but only on the source mass, I'm going to do the same thing here. And I'm going to say, well, the electric field, I only want to depend on the source charge and not on my test charge that I'm using to probe the field. So to get rid of the test charge, we're going to do the same thing we did before, and I'm basically going to divide the electric force by the test charge. And so I'm going to take something that depends on two charges and get rid of one of them. So I'm going to have something left, the electric field, that only depends on my source charge. So what does this mean? Well, so a couple of things here. One is, notice that we can sort of rewrite this equation and sort of think of it two ways, right? This is how we define the electric field, is it's the electric force per test charge. But we can also think of it in this capacity, which is, well, the electric force is just going to be the test charge you choose to bring into the electric field times the electric field itself. And this is probably, again, the more fundamental way to really think about what's going on, because the force that we actually see when we see charges attract and repel each other is really a fact of there is some test charge that is responding to the electric field generated by some source charge that's already present before I bring the test charge in there. So what is it that this tells us about how these two things relate? Well, let's start with the most basic. So again, the easy thing to do is to read this equation and say that the units of the electric field have just got to be units of force divided by units of charge, so that's got to be newtons per coulomb. So that's one way that we can write the units of the electric field. This equation, again, tells us that, well, if this is positive, anytime you take a vector and multiply it by a positive number, you can change its magnitude, but you don't change its direction. So if we use a positive test charge Q naught, then the electric field has to point in exactly the same direction as the electric force. If, on the other hand, we were to use a negative test charge, so if Q naught were negative, then the electric field would point in the opposite direction as the electric force. So that negative sign would cause these two vectors to point in opposite directions from each other. And so what we're going to do to take advantage of that is we're going to say, fine, we've got experience in terms of thinking about how charges feel electric forces, right? So we practiced, hey, you put a charge here in space and there are these other charges around. Well, is it going to be attracted to them? Is it going to be repelled by them? That's thinking about the forces. And so what we're going to do is we're basically going to always choose to place a positive test charge at the point P that you're interested in thinking about the electric field. And then, as long as we use a positive test charge, then thinking about the free body diagram, the forces felt by that positive test charge will give us exactly the same information as thinking about the contributions to the electric field of all those source charges that are generating forces on our test charge. So that's what we're going to do. We're basically just going to say we're going to figure out what's going on with the electric field by always using a positive test charge. So then in our example, so let's say that the charge Q, big Q that we started with on our very first slide, let's say it happens to be positive. Well, so I know that if I were to put a positive test charge at my point P, then it would be repelled. So there would be a repelling force. The electric force would try and push that positive test charge away. Well, since that's a positive test charge, that means that the electric field has to point in the same direction. So the electric field at point P is going to point away from my positive source charge, or positive big Q. If, on the other hand, the charge big Q that I started with, my source charge, if it happened to be negative, well, when I put my positive test charge at point P, it's going to be attracted. So now it's going to be pulled towards this negative charge, negative big Q. Since this is a positive test charge, it means that the electric field has to point in the same direction as the force that my test charge feels. So that means that the electric field has to point towards my source charge, negative Q. So this is basically the game that we're going to play in terms of thinking about the electric field at point P. So for point charges, so we know that the electric force between two particles with charge Q and Q naught, we'll let Q be the source charge, we'll let Q naught be the test charge, that are separated by a distance r, is given by this expression, right? Here's Coulomb's law. And so again, we've got the absolute value around our charges because this is just going to tell us about the magnitude, and r hat is going to end up telling us what we need to do to deal with directions. Well, to get the electric field, we know that we're going to take the electric force and divide by our Q naught. So what I need to do is take this expression and divide by Q naught, and it's easy to see that what's going to happen is this term will disappear, and I'm just going to be left with one Q on top. So again, the electric force depends on two charges. The electric field just depends on one, just depends on the source charge. Well, so this is a vector, and like any other vector, it's got both a magnitude and a direction. And so for starters, let's think about what the magnitude is saying here. And it says that the magnitude of the electric field is equal to, again, our Coulomb's constant, 8.9 times 10 to the 9th Newton meter squared per Coulomb squared, times the magnitude of the source charge divided by, and now r in this case is the distance from your source charge to the point P that you're interested in knowing the electric field at. So r has changed when we've sort of divided out Q naught. It's no longer the distance between Q and Q naught, it's now the distance between Q, your source charge, and the point P, which is where you're placing Q naught. Alright, so that's what's going on with magnitude. In terms of direction, well, that's really by our r hat. And so r hat here is telling us the same thing that it was in this situation. It's telling us that the electric field is directed along the line that runs between your charge and the point P. If your charge is positive, so if you've got a positive charge plus Q, then the electric field is going to point away. If you've got a negative charge, then the electric field will point towards your negative charge. So the first statement here is basically telling us about magnitude. The last three are telling us about the direction. And that we care about because, again, the electric field is a vector. And so if we've got multiple charges, then the way that we've got to deal with this, the way that we deal with multiple forces, is that we've got to add them together. So I need the vector sum, which in this case, what would I do? Well, let's see. If I put a positive charge here at point P, it would be attracted to this negative Q, which means that there's got to be a electric field contribution from my negative Q charge down here that's got to point along this line and towards that negative charge. There it is. If I put a positive test charge here at point P, it would be repelled by my positive charge here, so it's going to have so this positive charge is going to generate a contribution to the electric field that points along the line and away, so there's that contribution. I can calculate the magnitudes of these vectors by using my kq over r squared equation. And then now to add these up, well, I need to add them up as vectors. So graphically, tail to tip, adding these two vectors is going to give me something that points about here. And so this is just emphasizing that in the same way that we've been working, hey, the net electric force on some charge is a vector problem, well, the net electric field due to multiple charges is also a vector summation problem. And so we just need to add together the electric fields as vectors. All right. So the critical things that we sort of have to make sure that we come away understanding here. The electric field is a vector field. At any point P, the electric field can be represented by a vector. As with any vector, both the magnitude and direction of the electric field vector matter. And if we have multiple contributions, so multiple charges that are contributing to the electric field at some point P, then we've got to take the vector sum of all those contributing source charges to figure out what the electric field is at that point. This, of course, is called the superposition principle. We ran across this in 298. We've been using it so far in 299. We're going to use it again going forward. And again, it's just emphasizing that we need to add these things together as vectors. So at the end of the day, this is really just continuing what we've been doing so far this semester in terms of basically just working vector summation problems.